This lesson is about conditional probability. This little notation right here is the heart of conditional probability. This means the probability of event A given that event B has already occurred. As a quick example, look at this collection of shapes. We have some triangles and some circles, and some are yellow and some are green. We could talk about the probability of picking a green shape, and we might write that this way. All right, when we talk about probability, we think about target divided by total. In this case, the target would be the number of green shapes, and there are 4 of those, divided by the total number of shapes, which would be 10. So the probability of randomly selecting a green shape would be 4 over 10, which simplifies down to 2/5, which equals 40%. Okay, on the other hand, we could talk about the probability of picking a triangle. For example, again, target over total. The target would be triangles, and there are 5 of those out of a total number of 10 shapes. So of course that probability is 1/2 or 50%. Now here comes the conditional probability. We could talk about the probability of picking a green shape randomly given that we already know it's a triangle. That's what this notation would mean. So this second thing, the fact that we're given that we already know it's a triangle, that puts us in this world right here. We can forget about all of the circles. You know, I'm always saying target over total. Once you get down to a conditional probability, this first thing is the target, and the second thing is going to be the total. Okay, so target over total. So it's the number of green shapes, of which there are 2, out of a total of 5 shapes. Okay, because we're just dealing with the triangles, because we already know it's a triangle. So given that it's a triangle, the probability of picking a green one is 2 out of 5, which is 40%. Now here's one last thing, but it is very important. Notice how we got the same answer when I did the probability of picking a green, given that it's a triangle. All right, we got 40%. When we did the probability of picking a green shape, not knowing anything about what kind of shape it was, we also got 40%. Whenever that happens, we know that these 2 events are independent. We say that events G and T are independent if the probability of event G, given that event T is definitely true, is the same thing as the probability of event G anyway, without knowing anything about event T. In other words, if knowing something about the second event doesn't really change the probability, then those 2 events are independent. All right, one doesn't really affect the other. All right, so look at this first problem. If events A and B are independent, what must be true? Well, based on what I just showed you, if these events are independent, then, for example, the probability of event A, given this additional information that event B is definitely true, if these are independent, then this extra information doesn't actually change anything, and this will equal the probability of event A, you know, as though if we took the extra information away. It's just didn't really change anything. So that's one thing that we would know. Or we could switch it around the other way. If these events are truly independent, then we could start with the probability of event B. And we could say, okay, if we had this additional information that event A was also true, but that didn't really change anything. And that really just, the probability of event B is still the same regardless of whether or not you have the extra information. Either way, it's equal to the probability of event B without the extra information. Okay, so either of these things should be true if A and B are independent. So let's hunt for one of these two. Okay, so you see here the probability of event A given event B is equal to the probability of event A. That's the first one that we said right there. 25 bakery customers were surveyed to determine if they like cake or pie. Cake or pie. The results are shown in the Venn diagram. Alright, so we can see who liked cake, and we can see who liked pie, and we see who liked cake and pie, and a few crazy people didn't like cake or pie. That's weird. Who doesn't like cake or pie? Anyway, given that a randomly chosen customer likes cake, what is the probability that the customer also likes pie? So let's use our notation. Let's practice. So we're looking for the probability that the person likes pie. All right, the probability that the person likes pie. This double P makes me nervous. Given that the customer likes cake, all right? The randomly chosen person likes cake. We already know that. So that's the thing that we're given. So given that the person likes cake, so we're being asked, what's the probability that a person likes pie, given that we already know they like cake? And so look, as soon as you see that you're given some information, that becomes your universe. Right there, okay? So a person likes cake. So that means this is the universe. Okay, this is it. People who like cake. That's all that exists for me from now on. Just people that like cake. We're going to forget about everything else. Forget about all this stuff out here. Okay, it's gone. Forget about it. It's out of here. Alright, just focus your eyes on cake. Okay, because we're given that that's already a fact. Now, and you know what, I'm going to make this more dramatic for a second. Can I do highlighter in black, I wonder? Oh yeah, look at that. So, we're given that the person likes cake. So I'm going to black out everything else and just focus on the people who like cake. Now remember, as I do all this blacking out, see this little part of the circle that you can see in orange? Remember, that circle is from the people who like pie. Okay, this is that overlapping part though. But that's important because this number 4 still tells me people who liked pie. But they're also in the cake circle. That's why they didn't get blacked out. So if we want to know the probability of randomly picking a person who likes pie, then you know we're going to do target over total. All right, the target number divided by the total number. Okay, now the total number, as I emphasized by blacking out everything except for cake, we're given that the person already likes cake. So that reduces the total number down to just people who like cake. So we're not going to go with the original 25. Oh no, some of those people didn't like cake. We don't care about those people anymore. The universe is now 14 people who like cake. So when I talk about target over total, The total is now the 14 people who like cake. Now, out of the cake lovers, we're looking for the probability of picking someone who likes pie. So how many of these 14 cake lovers also like pie? Well, that's this number right here that's inside of this little part of the overlapping circle that we blacked out. All right, these are the pie people. So 4 out of 14, target over total. All right, and this is going to reduce down to 2 over 7. All right, let's see how that matches up with the answers down here. And there you go. The probability is 2/7. A study found that 23% of cars manufactured last year were SUVs. Okay, so SUVs, 23%. 13% of cars manufactured were white. Okay, so white cars, that's 13%. 2% of the cars manufactured were white SUVs. Okay, so white and SUV, that's 2%. To the nearest whole percent, what is the probability that a car is an SUV given that it is white? Alright, so we're given all this information and we're being asked to find the probability of randomly picking an SUV given that it is white. Now, here's the thing. When you're doing probability, we're always thinking in terms of target over total. All right, the target number divided by the total. Or in this case, percent instead of number, but still, same difference. Now, here's the key. When you're given something, this is what we are given. Okay, when you're given something, that becomes your whole universe. In other words, our target is SUVs, but our total is going to be white vehicles. All right, so when you're given a conditional probability like this, you're being given the target and you're being given the total. So in other words, white cars, that's what we're given. That is the total. All right, that's the whole, that becomes the entire universe at this point. So the total is 13%. Okay. Now here's the tricky part. Yeah, my target is SUVs, but my target is not just all the SUVs. It's just the white ones. All right. Remember, this is the universe now. We're only talking about white cars. Only white cars exist. So we're not talking about the 23% of SUVs that were made. We're just talking about the white ones. Okay, and that number is white right here. White SUVs. That's 2%. Okay, so we just want the white SUVs, not all of them. All right, so our target is white SUVs out of a total of the white cars. So that's going to be 2% out of 13%. All right, obviously 2% out of 13% is the same thing as 2 out of 13, which as a decimal is 0.154. And they want us to round this to the nearest whole percent. All right, to change this to a percent, you move the decimal point twice. So this would be 15.4%. So as far as the nearest whole percent, we're talking about 15%. So that should be the answer. And there you go. All right. We're given a Venn diagram and some conditional probabilities, but 3 of these are wrong and 1 of them is right. So we need to calculate these conditional probabilities and just look for the one that has the right answer. So let's just do these one at a time. Remember, when we look at something like this, probability of A given B, this second one, the thing that we're given, is the universe. Meaning we can forget about everything else except for this. All right, so for this first problem, we're trying to find the probability of A given B. So as soon as we see given B, here's what we do. We forget about, well, okay, remember that the blue circle here is A, okay? But other than that, we forget about everything outside of this. Okay, everything outside of B is gone. Only what is inside of B matters anymore. Okay? Forget about all of this out here. Okay, just focus your eyes on B, because that is the universe. So, in a universe where we're given that B is all that there is, now we want to talk about the probability of A. So, probability is always target over total. So we're looking for a target of A out of a universe of B. So remember that these are the A's in this B universe. So when we start doing target over total, we're going to look at how many A's we had in the universe of B. And we had 7, okay, out of a total of however many this is. Let's see, that's 10. The 9 and 1 is 10. 6 and 4 is another 10. So that's 20. So 7 out of 20. That does not match 1/2, so that's not the answer. Okay, this problem is good practice for us. We're going to do this over and over again until we fully understand. Okay, now we're looking at the second one. The probability of B given that A is definitely true. All right, again, that means A is now the universe. Okay, so let me go back and make A the universe. So I'm going to forget about everything outside of A. All right, forget about all of this. Okay, A is the universe. Now, when we talk about probability, we are still talking about target over total. So B is now our target in a universe of A. So B is our target. So I left this here to sort of remind us that this little part of the Venn diagram is still with B. So the 1 and the 6 are still part of B. But of course A is the universe, so we're only leaving them even visible because they are also in A. So target over total, target of B out of a total universe of A. So when we do that, we've got 7 out of a total of, let's see, that's 3 and 7 is 10. And then 6 and 1 is 7, so that's 17. So 7 out of 17. All right, this says 7 out of 20, so that's not going to be the right answer. All right, this is good practice. Let's keep going. Let's reset. Now, all right, the probability of A given C. All right, C is the universe. Okay, and we're shooting for A, so I'm not going to cover that up. But so C is the universe, so I'm going to sort of black out everything except for C. All right, none of these numbers matter. None of this matters. So target over total. Our target is A out of a universe of C. So the 7 and the 6 are members of A within this universe of C. So these are the targets, and C is the universe. C is the total. Okay, so 7 and 6, that's 13. That's our target. Our total, see, we've got 10 and we've got 13, so that's 23. Right? Yeah. So 13 out of 23. That is not the same as 6 out of 23, so that's not it. So I'm really hoping that this last one is the right answer, because that's all that's left. But let's check it out. Verify. Probability of C given A. Okay, again, A is the universe. Alright, it is the total. Okay, and C is our target. Alright, within that universe though, we still can't go outside the universe. So when I say C is the target, I don't mean all of C, just the part that's in the universe. So anyway, A is given A, so A is the universe. So once again, I'm going to black out everything except for A. Okay, so this is all gone. Alright, are you focusing on that? So I'm scribbling out all of this. Alright, I'm only leaving the C visible to remind you that this green circle was circle C before I blacked out the universe. So, target over total. Alright, C is now the target in a universe of A. So that's 7 and 6 is the target out of a total universe A. Okay, so target over total, 7 plus 6, that's 13. Out of a total universe A, that's 10 and 7, so that's 17. So that's 13 out of 17. Alright, and that does in fact match the final option. Kabam! Hero has a stack of cards with one number from the set 1 1 2 2 3 3 3 4 written on each card. What is the probability that he pulls out a 3 first and then pulls out a 2 without replacing them? Okay, it's this without replacing them part that lets you know that we're talking about conditional probability. Okay, now if it weren't for that, if they didn't say without replacing them, if they did replace them, then we would just use the multiplication principle, which would say that the probability of two events happening, so the probability of pulling out a 3 and pulling out a 2 would equal the probability of pulling out a 3 times the probability of pulling out a 2. Okay, that would be what we would do if you started fresh each time and you put back the card once you were done with it. Okay, now if you don't put the cards back, it affects the second one. Alright, it's going to change the probability from what it would normally be. So we're still going to basically do the same thing, but we're just going to be very careful to take into account that this second probability is going to be different than it would be if you put the cards back. Okay? So, let's think about it. The first one is completely normal. The probability of pulling out a 3. So we're going to just think target over total. So target is 3s, and we've got 1, 2, 3 of them. Okay. Now the total number of cards, we've got 1, 2, 3, 4, 5, 6, 7, 8. So that first probability is 3 out of 8. Okay. Now, we have to be really careful about this second probability, the probability of pulling out a 2, because we already pulled out a 3 first. That's already happened. So if you pulled out a 3 first, and we know that, the probability of pulling out a 2 afterwards is not going to be the same as it would be if we put this back. If we don't put this back, then we don't have 8 cards anymore. Now we only have 7. Okay, so the probability of pulling out this 2 under these circumstances is going to be target over total. We have 2 cards. All right, we have 2 2s, but out of a total of 7 cards, not 8. Now, technically, I need to change the way that I wrote the original problem, because if I just say probability of pulling a 2 just like that, it means the probability from the original situation. Okay, it means 2 out of 8 if I write it this way. So instead, to reflect the fact that we already know that the 3 is gone, the way you have to show that is, instead of just writing probability of 2, you have to say probability of 2 given that 3 has already been taken out. Okay, so technically I'm supposed to write it this way. So we found the probability of pulling a 3, and that was just normal because nothing had been taken out yet. And then the probability of pulling out a 2 given that the 3 thing already happened. That looks like a 13. I don't like that. Let me change it. In fact, I'll just use green. Now what? All right, but that's just the way you write it to show what we did by taking into account that we took a card away, so it was only going to be 2 out of 7 and not 2 out of 8. Anyway, we're going to go ahead and multiply these together, and that should give us the probability. Okay, 3 times 2 is 6. 8 times 7 is 56. And this will reduce down to 3 over 28. Okay, and we can make that into a percent or decimal or something if they want us to. All right, 3 out of 28 seems to be just fine. A bag contains 1 red pen. All right, let's see, we have 1 red pen, 4 black pens, and 3 blue pens. Okay, 2 pens are randomly chosen from the bag and are not replaced. As soon as you see that it's not replaced, that's how you know that we're dealing with conditional conditional probability. I had to really think about how to spell it. So just be careful. We're picking 2 pens, but because we're not replacing, when you pick the second pen, the probability will change. So here we go. We're trying to find the probability of picking a black pen and another black pen. Now, normally, if you put the pens back and started fresh each time, then this would just be the probability of picking a black pen times the probability of picking a black pen. That's what it would normally be. But because we are not replacing the pens, when we do the second one, we have to be very careful because the numbers are going to change. Okay, so let's go through it. The probability of picking a black pen. Let's talk about the total number of pens. Let's see, we have 7, 8. We have 8 total. So the probability of picking the first black pen, target over total, there are 4 black pens out of a total of 8. Now let's talk about the probability of picking the second black pen. It is not going to be 4 out of 8 again, because one of the black pens are already gone and we are not replacing it. So because one of the black pens are already gone, now there are only 3 black pens left at this point. And because we took away one of the pens, there are not 8 pens anymore. There are now 7. So when we go to grab the second black pen, there are 3 targets out of a total of 7. So that's where your conditional probability happens. Okay? Now before I go any further, technically I have to rewrite the second one, because if I just put the probability of grabbing a black pen, that means 4 out of 8. Right? Written that way, it means from the original setup. If I want to somehow reflect the fact that something has happened ahead of time, that's what conditional probability is, and I need to write it this way. So I can't just say the probability of grabbing a black pen. For the second one, I have to say the probability of grabbing a black pen given that a black pen was already chosen. Okay, so really I should write it that way, but this extra information on the end is just a reflection of what we did here by changing the numbers. Instead of 4 out of 8, we recognize that because one pen was taken away and not put back, those numbers became 3 out of 7. Alright, that's all this means. So now we can go ahead and finish the problem. Of course, 4 out of 8 is really just 1/2. So it's 1/2 times 3/7. 1 times 3 is 3. 2 times 7 is 14. So 3 out of 14. Now this time they said the nearest hundredth, so that means they want a decimal. So 3 divided by 14 . Okay, that's 0.21. Or 21%. Okay, kabam. "75% of the flowers in the arrangement are roses." Okay, so roses, 75%. And the rest are tulips, so that means tulips, 25%. Of the tulips, 50% are pink. Okay. To the nearest whole percent, what is the probability that a randomly chosen flower from the arrangement is a pink tulip? A pink tulip. Well, let's just use common sense on this one, guys. 25% of the flowers are tulips, and then half of those, 50% of those, are pink. So if you take half of 25%, that is 12.5%. Okay, which should round to 13%. All right, let's not make it more complicated than it needs to be. In the drawing, 6 out of every 10 tickets are winning tickets. Okay. So, winning tickets, 6 out of 10, or 60%, or 3 out of 5. Of the winning tickets, 1 out of every 3 awards is a larger prize. So, of the 60% that are winners, a third of these are larger prizes. What is the probability that a ticket is randomly chosen will award a larger prize? Well, that's a matter of what is 1/3 of the 60%. Okay, so let's just do that calculation. What is 1/3 of the 60%? Okay, or I could have left it as a fraction and done 1/3 of 3/5, which is probably simpler because 1 times 3 is 3, 3 times 5 is 15, and this reduces down to 1/5. Or I could have just canceled these 3's out, 1/5. And 1/5, that would be the answer in fraction form, which is the same thing as 20% or 0.2, depending on which way you want to go with it. They went with the 1/5, so there you go. Guys, I hope this video was helpful to you. Good luck on your quiz.